Transcoders beat Sparse Autoencoders for Interpretability by John Paulo, Stepan Shabalin, and Nora Belrose. Abstract. Sparse autoencoders extract human interpretable features from deep neural networks by transforming their activations into a sparse, higher dimensional latent space, and then reconstructing the activations from these latents. Transcoders are similar to SAEs, but they are trained to reconstruct the output of a component of a deep network given its input. In this work, we compare the features found by transcoders and SAEs trained on the same model and data, finding that transcoder features are significantly more interpretable. We also propose skip transcoders, which add an affine skip connection to the transcoder architecture, and show that these achieve lower reconstruction loss with no effect on interpretability. Introduction. Recently, large language models have achieved human-level reasoning performance in many tasks. Interpretability aims to improve the safety and reliability of these systems by understanding their internal mechanisms and representations. While early research attempted to produce natural language explanations of individual neurons, it is now widely recognized that most neurons are polysemantic, activating in semantically diverse contexts. Sparse encoders, SAEs, have emerged as a promising tool for partially overcoming polysemanticity by composing activations into interpretable features. SAEs are single hidden layer neural networks trained with the objective of reconstructing activations with a sparsity penalty, sparsity constraint, or an information bottleneck. They consist of two parts: an encoder that projects activations into a sparse, high-dimensional latent space, and a decoder that reconstructs the original activations from the latents. Bricken, etc., introduce a technique of evaluating the interpretability of SAEs by simulating them with an LLM-based score, similar to what had been done on neurons. This approach is commonly called automated interpretability, or autointerp. SAE features perform much better on this benchmark compared to neurons, even when neurons are sparsified, by selecting only the top K most active neurons in a layer for analysis. One problem with SAEs is that they focus on compressing intermediate activations rather than modeling the functional behavior of network components, like feedback or feed-forward modules. Transcoders are an alternative to sparse autoencoders, initially proposed in Lai, etc., and Templeton, etc., and first rigorously evaluated by Dunfsky. Unlike SAEs, transcoders approximate the input-output function of a target component, such as an MLP, using a sparse bottleneck. Dunfsky, etc., demonstrate that transcoders enable fine-grained circuit analysis by learning input invariant descriptions of component behavior, complementing automated circuit discovery tools like CONME, etc. Transcoder design faces inherent challenges. While ReLU MLPs carve up the input space into polytopes, with each polytope corresponding to a relatively high-rank linear function, transcoders' sparse activations mean that each activation pattern corresponds to a low-rank linear transformation. Furthermore, since Marx, etc., and Bricken, etc., new benchmarks for sparse features evaluations have emerged, Carvan, Zhuang, etc., motivating a broader evaluation of transcoders across models and tasks. We investigate the trade-off between reconstruction error and interpretability by comparing SAEs and transcoders, and address challenges mentioned above by proposing an architectural improvement, the skip transcoder, which mitigates rank limitations via an affine skip connection. In this work, we introduce skip transcoders, which reduce reconstruction error without compromising interpretability, compare transcoders, skip transcoders, and SAEs across diverse models, up to 2 billion parameters, showing skip transcoders Pareto dominate SAEs on reconstruction versus interpretability trade-offs. And lastly, evaluate transcoders on SAE bench demonstrating improved quality in both latent level phenomena like absorption and performance on various tasks through sparse probing. We conclude that interpretability researchers should shift their focus away from sparse autoencoders trained on the outputs of MLPs and toward skip transcoders. Methods. Skip transcoders add a linear skip connection to the transcoder, which we find improves its ability to approximate the original MLP at no cost to interpretability scores. Specifically, the transcoder takes the functional form f of x equals w of 2 times the function top k of w of 1 times x plus b of 1 plus w of skip times x plus b of 2. Both w of 2 and w of skip are 0 initialized, and b of 2 is initialized to the empirical mean of the MLP outputs, so that the transcoder is a constant function at the beginning of training. We leave a deeper analysis of the skip connection, perhaps interpreting it using SVD for future work. Training. We train a collection of sparse encoders, sparse autoencoders, sparse transcoders, and sparse skip transcoders on the MLP layers of Pythia 106 million. We also train SAEs and SSTs on Llama 3.2 1 billion and Gemma 2 2 billion. We train with mean squared error between the output of the sparse coder and the MLP output with no auxiliary loss terms. Unlike prior work on transcoders, we adopt the state-of-the-art top K activation function proposed by Gao, etc., which directly enforces a desired sparsity level on the latent activations without the need to tune an L1 sparsity penalty. We sweep across K values of 32, 64, and 128 in our experiments. For sparse coders trained on Pythia, we train over the first 8 billion tokens of Pythia's training corpus, the pile. For the other models, we use 8 billion tokens on the Red Pajama V2 corpus. All sparse coders are trained using the Atom Optimizer, a sequence length of 2049 and a batch size of 64 sequences. Evaluation. We use the automated interpretability pipeline released by Palo, etc., to generate explanations and scores for sparse coder latents. Activations of latents were collected over 10 million tokens, sampled from the pile for the Pythia models and from FineWeb for Llama and Gemma. The explanations were generated by showing an explainer model, Llama 3.1, 70 billion parameter, 40 activating examples, 4 from each of 10 different quantiles. Each example had 32 tokens, and the active tokens were highlighted. Detection and fuzzing scores were computed over 50 activating examples, 5 from each of 10 different quantiles, and 50 non-activating examples. Simulation scores were computed over the same 50 activating examples, as described in the link. The score model was Llama 3.1, 70 billion parameter. We also use the SAE bench repository to evaluate the sparse coders. We use it to compute the variance explain and the cross-entropy loss increase over 500 tokens of the open web text corpus. SAE bench also provides the ability to train and evaluate sparse probes that measure the ability of SAE's encoder to select information relevant to classification tasks such as sentiment and language detection. Recently, Channon, etc., drew attention to the phenomenon of feature absorption. In some cases, a more general feature like starts with the letter L appears alongside a specific feature like the token lion, which may prevent the general feature from being active in contexts where intuitively both the general and the specific feature apply. They argue that this is undesirable. We use SAE bench to compute the frequency of absorption of general letter features to specific features in SAEs, STs, and STSs. Skip transcoders Pareto dominate SAEs. The utility of any sparse coding method for interpretability lies in its ability to accurately reconstruct activations while also generating human interpretable latent features. This is a fundamental trade-off. While sparser latents are generally more interpretable, higher sparsity also tends to increase the reconstruction error. The reconstruction error of a sparse coder can be viewed as dark matter, containing features not captured by the latents. Following earlier work on SAEs, we can represent this trade-off using a reconstruction versus interpretability curve. Here we compare the reconstruction loss of different models, varying the number of latents and sparsity with their interpretability scores, measured as the average between detection and fuzzing score over a set of features. We find transcoders and skip transcoders with the same number of latents generally have higher interpretability scores for the same reconstruction loss than SAEs. Not only are the average interpretability scores of transcoders and skip transcoders higher than those of SAEs, but their distribution is narrower. Latents of skip transcoders also seem to represent more monosemantic features, as the explanations found hold for a larger portion of the activation distribution. This can be seen by comparing the accuracy of explanations in examples sampled from different quantiles of the activation distribution. The accuracy of explanations decreases more slowly for STs and SSTs than SAEs. The explanations also are more sensitive as the false positive rate is lower. We replicated these results in models of the same architecture but different sizes. Pythia 160 million parameter and Pythia 410 million on larger models with different architectures. Llama 3.2 1 billion parameter and Gemma 2 billion parameter. On all cases studied, SSTs had higher automated interpretability scores and lower CE loss increase when patched in. We found that performance on sparse probing was similar for SSTs and SAEs, with SSTs winning out for later layers by a small margin. Sparse probing measures the ability of SAEs to preserve information in the original latent, but for transcoders, the latent should relate more to concepts necessary for processing the input. It is thus surprising that they are competitive with SAEs on compressing the residual stream without being trained with that objective. We also find that SAEs and transcoders have similar feature absorption behavior, but that those results are noisy. We don't expect this to be a problem since there are other methods orthogonal to ours which seem to improve feature absorption. See discussion in section 5. Conclusion. Our experiments suggest that interpretability researchers should shift their focus from sparse autoencoders trained in the outputs of MLPs to skip transcoders. In our view, the only downside of transcoders compared to sparse autoencoders is that SAEs can be trained directly on the residual stream, while transcoders need to be trained on particular components of the model, usually a feed-forward layer. However, one can easily convert a strip transcoder trained on an FFN into a residual stream transcoder by adding the identity matrix to its skip connection. In this way, skip transcoders can be viewed as bridging the gap between these two types of sparse coding. Additionally, it is known that SAEs trained on nearby layers in the residual stream learn very similar features, effectively wasting training compute, while SAEs trained on nearby FFNs learn disjoint sets of features. For this reason, we suggest that practitioners who are planning to train more than one sparse coder on a model should consider training transcoders on FFNs in lieu of SAEs on the residual stream. Future work. As we have shown, transcoders preserve more of a model's behavior and produce more interpretable latents. We believe skip connections let the transcoder avoid the redundant work of translating the linear map, letting it focus on learning important features. Future work may illuminate the role of the skip connection by comparing it to a learned or analytically derived affine approximation of the MLP component. Doomsky, etc., highlights the usefulness of transcoders for circuit detection. While we have not run experiments on circuit analysis like in that paper, we expect that skip transcoders to be better for reconstructing circuits thanks to their lower reconstruction error. It is unlikely that the skip connection impedes gradient-based circuit discovery. Work like Marx, etc., shows ways of incorporating linear skip connections into circuit discovery faithfully. Transcoder and skip transcoder features may be used for steering, but we could not translate the unlearning and concept erasure benchmarks from Karen, Carvonen, etc., which requires the latent to contain all information in any given residual stream position. Transcoders also do not help improve the feature learning in SAEs the way new architectures like GAO do. They merely change the objective of the SAE, which is something that cannot lessen inefficiencies in training. We see the effects of this in the evaluation results on feature absorption. Transcoders and skip transcoders can exhibit it just as much as SAEs. Furthermore, feature density plots do not exhibit significant differences. Appendix B, showing that SAEs and SSTs are similar on a mechanistic level. Work like Matryoshka SAEs may help tackle these issues for both SAEs and SSTs. My summary. This paper shows that transcoders do a better job than regular sparse autoencoders at revealing how large language models work on the inside. Instead of simply compressing internal activations, transcoders learn to mimic the input-output behavior of model components, which turns out to produce more interpretable features. Adding a skip connection, making them like skip transcoders, further improves accuracy without hurting clarity. The upshot, if you want clear insights into what your model is doing, consider skip transcoders over standard sparse autoencoders.